Hello, good day. So for our presentation, we will be talking about one of the most important lessons in calculus, the continuity of a function. Let's start by defining the concept so we can consider that a function is continuous if we can draw its graph without lifting our pencil from the paper. Mathematically, a function f of x is continuous at a point x equals c if three conditions are met. F of c is defined, the limit of f of x as x approaches c exists, the limit of f of x as x approaches c is equal to f of c. For example, consider f of x is equals to x squared at any point say x equals 2. F of 2 exists and equals 4. The limit of f of x as approaches 2 also equal 4. Since both values are equal, f of x is continuous at x equals 2. Types of discontinuity. Not all functions are continuous. A function is discontinuous at a point if it's not continuous at the point. This means the function graph has a break, hole, or a jump. That specific x value. There are different types of discontinuities. Removable discontinuity, a hole in the graph. Jump discontinuity, a sudden jump in values. Infinite discontinuity, when the graph goes to infinity like in x equals to 0. Why continuity is important? Continuity is important because many concepts in calculus such as derivatives and integrals only work in function is continuous. It ensures smooth, predictable behavior of the graph. So in short, a continuous function is smooth with no breaks, jumps, or holes. Next, let's move on to how we can actually find derivatives.
Now, we move on to our next lesson, which is the derivative of a function. Before we begin, let's first start to define the derivative of a function. Because in simple terms, it represents the instantaneous rate of change of a function at a specific point. So, in order to get the derivative of a function, first, we transform y into f of x. Then the next step, step 2, give x an increment delta x. Then y takes increment to corresponding delta y. Basically, it will become that y plus delta y is equal to f of x plus delta x. Step 3, we solve for delta y. Delta y is equal to f of x plus delta x minus f of x. So basically, we transposed the y into the other side and it will become f of x because f of x is equal to y. For the step 4, we divide delta y with delta x, which is the average rate of change. And for the last step, we now turn into f prime x is equal to limit of delta y divided by delta x as delta x approaches 0. For example, for our example, find the derivative of f of x at x squared. So for the first step, we transform y is equal to f of x. For the second step, we state that y plus delta y is equal to f of x plus delta x. For the third step, delta y is equal to f of x plus delta x minus f of x. We transpose the y in order for it to become f of x since y is equal to f of x. For the second part of this step, we will substitute f of x is equal to x squared. So it will become x plus delta x squared minus x squared. After this, we distribute the squared in the quantity x plus delta x. So it will become x squared plus 2x times delta x plus delta x squared minus x squared. It will become delta x times 2x plus delta x. For the first step, we divide delta y by delta x. So it will become delta y divided by delta x is equal to delta x times 2x plus delta x over delta x. This will become delta y over delta x is equal to 2x plus delta x. For the fifth step, since delta y and delta x over delta x is similar to f prime of x, so f prime of x is equal to limit of delta y over delta x as delta x approaches 0. If we will substitute, it will become the limit of 2x plus delta x as delta x approaches 0. It will become 2x plus 0 or just 2x. So those are the 5 steps for finding derivatives. They're the foundation of differential calculus, allowing us to calculate slopes, rates of changes, and much more. Thank you for listening.